Thank you very much. I'm very excited to be able to tell you about this experimental program, which is actually something that we're just beginning. So it was something that was recently supported by a new government grant to a large consortium, which included Lancaster University. And what I'm going to tell you about today is what dark matter is and how we hope that by using quantum technology, we might be able to find it. Let me start off by trying to summarize the entire history of the universe in one slide, because this is how I can explain what dark matter is and why we believe it exists. So the universe began 13.8 billion years ago with the Big Bang, and all of the matter that we have in the universe exploded from one very dense initial state. And then over the course of the next 13.8 billion years, then stars formed and galaxies formed. And in those stars, then the initial hydrogen of the early universe was converted into other elements, which allowed chemistry, and therefore the formation of our planet Earth and other things that we know and love, life on Earth, and eventually Lancaster University itself. So that is the universe. So the universe at the moment is full of empty space and galaxies. And in almost any direction that we look, then there are galaxies pretty much as far as we can see, unless there's something in the way. It's estimated that the total number of galaxies within range of our telescopes is something like 2 trillion. This is some small section of sky in which the Hubble Space Telescope has just looked to see what there is. So the whole universe, as far as we know, looks something like this. And the fantastic thing is that all of those galaxies and distant stars, as far as we can see, are made of the same materials, the same atoms that we have on Earth. And we know this because we can look at the spectral fingerprints, which is to say the wavelengths of light that get absorbed, and they're the same as the absorption features of hydrogen and other elements on Earth. So if we take a galaxy at random, this is one whose image happens to be on Wikipedia, then you can look at it and you can see there's a certain amount of stars in there, and a certain amount of dust, and a certain amount of interstellar gas. So this is fantastic that we know what even distant galaxies are made of. But the mystery is what we can see of those galaxies is only 16% roughly of the total matter that's there. 84% of what a galaxy is made of, every galaxy, including ours, we don't know what it is. It's dark matter. It's dark because we can't see it through our telescopes, and it's also dark in the technical sense that it doesn't interact strongly with any of the experiments that we've built on Earth. So what makes me so confident to make this bold claim that 84% of the galaxy is invisible to us? Well, this comes from a very careful measurement of the orbits of stars around a galaxy. In every galaxy, then the stars are moving, of course, so they're orbiting around the center of the galaxy. And just like for a satellite orbiting Earth, the gravitational pull of the Earth controls the speed at which the satellite orbits. In a galaxy, the gravitational pull of the inside of the galaxy controls the speed at which satellites orbit around the edge. And so the calculation is fairly simple. We do it in first year classical mechanics to work out from the measured speed what the mass ought to be and what the galaxy is, what the mass is, as far as we can see. And this gives us this enormous discrepancy. So this is something that's really highly embarrassing, I would say, that almost all of what matter is made of, we have no idea, really. We have almost no idea what it is. And this is something that was discovered within living memory. So until the 1970s, people lived in blissful ignorance of this. This is Vera Rubin, who first made the first careful measurements of these galactic rotation speeds and was able to show, surprisingly, that there was such an enormous amount of missing matter. So this gives us a great challenge for physics, which is to work out, what is every galaxy, including our own, made of? What the data is telling us is that as well as the visible part of each galaxy, there is an invisible part, a halo, which is some kind of cloud around it. And the composition of that halo is something that we're trying to find out. Now, I should say, even though the mass involved is very large, the density is very low. So the dark matter halo, its mass density corresponds to roughly 1 hydrogen atom for every 3 cubic centimeters of space. So although over the galaxy as a whole, it's a lot, in any one place, it's some very small amount of matter and therefore quite difficult to detect. But the hypothesis is, whatever it is, it's probably some kind of particle. It's definitely something we haven't discovered. And the only thing we know for sure about it is that it interacts very weakly with ordinary matter. So what could this particle be? Well, there are many ideas, but the most convincing ideas, the ones that have found the most acceptance in physics, is that whatever particle it is, it should solve some other problem in physics as well. And there is such a problem. There is a problem in particle physics called the strong CP problem, which is about the symmetries that fundamental particles have. Now, unfortunately, there is no simple way to explain this within one slide. So I will simply say that it involves the fact that if you take a subatomic particle, an electrically neutral subatomic particle, and you measure the charge distribution that you find is very different from what you should expect by what we know about classical physics, about the standard model. And you can explain this by doing a lot of quantum field theory and by postulating the existence of an undiscovered particle called the Axion. So the Axion dark matter hypothesis is that this Axion exists, that shortly after the Big Bang, enormous numbers of axions were created in the universe. And over the course of the evolution of the universe since then, they've cooled down and they've congregated in every galaxy, including our own, and they're orbiting in this galactic halo. And if this model is correct, then some very large number of axions, by one estimate 10 to the 24, so a trillion axions are passing through you every second, but not interacting. So it's something that you have to find, even though it passes through ordinary matter almost without trace. So how can we look for axions? Well, there's many uncertainties in this field, but one thing is absolutely clear from the standard model of particle physics, which is if axions exist, the way to make them visible is to convert them into something you can see. And the way to do that is to pass them through a magnetic field. So the experiment that you want to do is to take the biggest magnet you can build. You have for free a flow of axions through that because they're in the galactic halo. And what the standard model tells you is that these axions, with some small rate, convert themselves into photons. A photon is a particle of light, and photons we know how to detect. And it also makes the prediction that if the axion has a mass m, then the photon that gets created has to have the same energy, so it's E equals mc squared. That tells you the energy of the photon. And then you also can know its frequency from that as well. So C and H are fundamental constants of nature. Whatever the mass is, you know immediately what the frequency you should be looking for. The problem is we don't know the mass of the axion. So what we have to do is to make some kind of detector that will detect this very weak source of photons and look. And if we find them at some particular frequency, then we know the axion exists and we know what its mass is. If we don't find them, then we can exclude the axion as being the explanation for dark matter. So this kind of instrument is called a haloscope. It's called a haloscope because it looks at the galactic halo. This is the basic idea. What you do is you need you build your magnet, first of all. That's the blue coil here. Inside that, you put some kind of chamber that reflects radio waves. So the idea is when the axions come in, they convert to photons. We believe the photons will have a frequency that's in the radio range, so it's radio frequency light. Inside this cavity, this chamber, they will bounce around, and then they'll get detected by an antenna. We amplify them, and then we look at the frequency of what comes out. And what we hope for is there is one frequency where the amount of power that's coming out of our chamber is much higher than all the other frequencies, and that will be the sign that the axions are in there. So that's in principle what the experiment design is. This is an example of an actual instrument. It's the Axion dark matter experiment in the United States. This copper cylinder here is the radio reflecting chamber, and when this is running, this all sits in liquid helium to be extremely cold, and they monitor the signal that comes out. And so far, I should say, they've searched been running for the experiment in a while. They haven't found the axion yet, but that's because they've only searched some part of the parameters of the frequencies where it might exist. So why do we believe we can do better? The really important thing in any haloscope experiment is the electronic amplifier. A haloscope is rather like a radio. In a radio, you have a radio wave from a radio transmitter that gets picked up by your antenna, and then you have an amplifier inside your radio that converts the small signal that comes in to a large signal that goes out, and that then you hear through your speaker. In an axion, you have some small signal that gets created from the axions that gets amplified, and then the signal, instead of going to a speaker, it goes to a spectrum analyzer. But you can see that just like in a radio, you want to amplify the signal as much as you can, increase the signal, but to do that with the minimum of noise. And in this case, we have an extremely weak signal, so we need a very good amplifier. And we have such a thing. This is a photograph of one of the refrigerators we have in the low temperature lab. Inside it, there is a very low noise amplifier, a superconducting amplifier. This one comes from Finland. It sits inside this metal cavity here, and it has much better performance than the amplifier in your radio, or in fact, any kind of amplifier that you can build using transistors. And we are, as part of this project, we'll be making them. This is the Lancaster Quantum Technology Center, where we make electronic devices, including superconducting amplifiers. These people are wearing clean room suits to prevent any dust from them falling onto the amplifiers and damaging them. Now, what makes this quantum is there is an ultimate limit on any electronic amplifier, which is set by the quantum uncertainty principle. If you took A-level physics, then you will know there is an uncertainty in any quantum measurement. If you try to measure position and momentum at the same time, then you cannot do that, because the more precisely you measure one, the more you will disturb the other. The same is true for electronics. So any electronic signal, any voltage, is a combination of a cosine signal and a sine signal. The closer you measure one, the more you disturb for the other. And the analog of the uncertainty principle in this case is the error, the uncertainty in these two signals. If you multiply the product of those two, has to be bigger than something proportional to Planck's constant. So probably, in general, you expect the uncertainty on the sine and the cosine to be the same. You don't normally expect to be able to distinguish them. And so this sets the ultimate limit on how precise the amplifier can be. And this is limited by the fundamental laws of nature, by quantum uncertainty. Now, what is true about axions is the signal itself is small, but it's not that small. It's something we can detect. So if God himself was to tell us tomorrow what the mass of the axion exists and what its mass is, and if it's within the frequency range of our current haloscopes, we would be able to calculate the frequency, tune the haloscope to that frequency, and then we would know in a few minutes whether that message was authentically divine. Unfortunately, we don't have a message from God. We have to make do with the second best thing, which is theorists, and different theorists give you different answers. But one plausible range is that the axion will exist between about 3 billion hertz. Its frequency will be somewhere between 3 billion hertz and 8 billion hertz. And to search that entire range, limited by quantum mechanics, would take 500 years. So that's clearly a silly experiment to do. However, there is a very clever technique, which unfortunately I don't really have time to explain, which is that you can circumvent quantum uncertainty by building an amplifier that amplifies only one component, only the sine component, and not the cosine component of the signal. I can explain this in the questions if you want me to. But if you do that, and this is what we are trying to do, then you can escape this quantum trap and possibly reduce this 500-year experiment into something more like a 5-year experiment where you could hope to know the answer within the duration of your career. So this is what we're doing. These are some cryostats in Lancaster. We have a large number of fridges that get extremely cold, so we know how to do that. And we're working on developing the amplifiers as well. And as I say, this project has just started. I should add there are actually 2 experiments going on in Lancaster to look for 2 different possibilities for dark matter. If you want to hear about the other one, then I suggest you invite one of my colleagues back for this conference next year. But that brings me to the end of the talk and the summary. So dark matter exists. If anything we understand from astronomy is correct, there seems no way to avoid this conclusion. It may well consist of axions. If so, we should try to detect them using a haloscope. And if we can build a quantum amplifier, then we can make a haloscope efficiently and therefore have a chance that axions will be found, even better, that axions will be found using an experiment built in Lancaster. Thanks for your attention.